Hello everyone, in this short lecture I am going to demonstrate how to use the Power World simulator to simulate and study the steady state stability limit of a thermal power station which supplies power to a variable load. Here the figure shows the model of our problem. This is our thermal power plant which supplies power to the variable load and have over a transmission line of length 300 kilometer long and a series which is having a series reactance of 0.34 ohms per kilometer and 4.5 into 10 to the power of minus 6 Siemens per kilometer. Our system operating voltage is at the voltage of 500 kilovolt. And here in this problem we are going to identify the maximum power that the generator can supply to the load, and also we are going to identify the angle at which the system becomes blackout. Here the figure shows the power angle curve of a power system. X-axis represents the power angle variation from 0 to 180 and y-axis represents the variation of the power. It reaches maximum at 90 degree and again reaches 180 degree. These three equations we are going to use for our calculation. The first one is SIL, surge impedance loading. It is equal to V rated square over ZC. ZC is the surge load impedance of a lossless transmission line. The Pmax is the maximum power, that is the maximum power that we can transmit over this line to the load. Before we verify the problem using the Power World simulator, let me take a numerical example. Here I am taking Vs and Vr both equal to 1 per unit at the rated voltage of 500 kilovolt. Using the above formulas, we can find these two values, SIL and Pmax. SIL is the surge impedance loading, as this one is related to this curve and this one related to the above curve. The first one we see this SIL. SIL is the surge impedance loading. As if our load is at this value, then Vs equal to Vr. The sending end and receiving end voltage, both voltages are equal, and the net reactive power flows in the line, it is equal to 0. And if the load is less than this SIL, then the receiving end voltage is more than the sending end voltage. If our SIL is more than if the load is more than SIL, then the receiving end voltage is lesser than the sending end voltage. Here we can see the variation of voltage in this graph. Now we come to the next one, the power max. How much the maximum power that we can transmit over the transmission line to the load. If we consider the angle theta equal to 90 degree, this is the maximum power that we can generate and transmit. But Pmax is limited up to 45 degree. Why it is up to 45 degree? Come to this above graph, we can see here the theoretical steady state stability limit and practical steady state stability limit. Here the theoretical steady state stability limit is very high, practical steady state stability limit is less. We can see here for the length of 300 kilometer for our problem, here the practical is very less compared to the theoretical one. It is around 1.4 times the SIL, the value, or 1.5. We get around the value of 1364. This is the practical line loadability. Theoretically it is more, but practically it is less. And also the angle we note down, it is around only 45 degree, not 90 degree. If we operate our system more than 45 degree, the system reaches a steady state stability limit and the complete blackout will happen. Now we verify our result using the Power World simulator. Go to draw network bus. In our model, we are using two buses. Both are operating at 500 kilovolt. Generator 1 is connected at bus 1. Load is connected at bus 2. Here I take 100 megawatt load. Transmission line is connected between bus 1 and 2. Calculate impedance from per distance impedance. Here I take kilometer, length units is in kilometer. In our problem we are taking 300 kilometer length and reactance is 0.34, shunt admittance 4.5 into 10 to the power of minus 6, and the base MVA is 100 MVA, base voltage is 500 kilovolt. Now go to online. I want to visualize both actual and reactive power flow in the line. Go to draw field, bus field, voltage, bus voltage. I want to note down the voltage at both the end. And the angle at both the end. Now we run our model. Go run. In this problem, based on this load, we can see the variation of the voltage at the receiving end and the reactive and active power flow from the generator and towards the generator. Here now the load is 100 megawatt. In our problem we are taking surge impedance loading. It is equal to 909.4 megawatt. 909.4 is the surge impedance loading. Now 100 megawatt is less than our surge impedance loading. For this less value, we can identify the voltage at the receiving end is more than the sending end. It is because of the capacity effect. And here we can see 100 megawatt is the power generated by the generator and it's supplied to the load, and minus 350 megavolt ampere, it is the power flowing towards the generator, not from the generator. So it indicates the power is reactive power and it is supplied to the generator, not generator supplying the reactive power to the line. This is totally the capacitive reactance because of the capacitive reactance and capacitor effect. Now we increase the load 500 megawatt. For 500 megawatt, we can see here the load voltage is reduced, but still the reactive power is flowing towards the generator, not from the generator. Now we put the load of surge impedance value. As at this load, we can see the receiving and sending end both voltages are equal, and the net reactive power flow in the line is also 0. Only the active power flow from generator to the load. Here 0 MVAR, here 0 MVAR. The MVAR flow, you can see that blue color arrow, now it is 0. At the surge impedance loading, now the net reactive power flow that is inductive and reactive, both are equal and it is equal to 0. So it is the load, it is called natural load. At this load, the reactive power by the capacitor and the inductor both are equal. It is called the impedance loading, surge impedance loading or natural load. Now we increase the power more than the surge impedance loading, 1100. Yes, now we can see the voltage at the receiving end is started reducing, and there is reactive power flow from the generator towards the line. Still the load side MAR is 0. According to our problem, practical line load ability is 1364. Now we increase the load and see the variation. Now I increase the load. You can see the voltage at the receiving end is reducing and the power angle also increasing, and the reactive power from the generator is also increasing. So now we are going to find the steady state stability limit of this model. We are increasing the load and identified at 1350 megawatt at the angle of 45. The 45 is the steady state stability limit. Though we can go up to 90°, but if we connect the load and the reactance of the line and considering the reactance of the generator, as here the power angle is limited up to 30 to 45°. If we supply more than 45°, the system becomes unstable. Here the table shows the solution of the above problem. To understand this table, we take SIL value. The SIL is the load. At this load equal to SIL, if the load is equal to SIL, and the voltage at the receiving end Vs equal to VR, both same, Vs equal to VR, and the net reactive power flow in the line, it is equal to 0. If we take our load less than SIL, the receiving end voltages are more, and also the reactive power supplied by the generator is 0, and the reactive power towards the generator is slowly decreasing. If we take more than SIL, the voltages keep on decreasing and the reactive power supplied by the generator is increasing and the load is slowly increasing with respect to the power angle. We conclude here at the angle of 45°, the system becomes unstable. Unstable means here up to 45° the system can supply the power, but at the angle of 45° the system reaches the unstable state. That is the steady state stability limit. If we want to operate our system, we should operate between this 21 to 34, around 40°. Not more than 40° is not advisable. And here the power steady state stability limit, the power maximum power we can transmit is around 1348, not 348. We can go up to 1300.